The next area of work that we're looking at in topic 3.1 on gravity and motion is circular motion. You can see the dot points that we'll be dealing with as we go through this video. As the name suggests, circular motion involves the movement of an object as it travels on a circular path. So I'll just write that fairly obvious statement first. So movement of an object along a circular path. Now, the sorts of scenarios that you might think about there are things like a Ferris wheel, turning the corner in a car, the drum in a washing machine that spins around in a circle, particles in the Large Hadron Collider move on a circular path as well, and even, say, a ceiling fan, the blades of the ceiling fan moving in a circular path. We are specifically going to look at one subsection of circular motion, though. We're not going to try and cover everything because it's just a little bit too broad in scope. We're going to specifically look at uniform circular motion. So uniform circular motion, so the emphasis here on the word uniform, is the specific case where the speed of the object is constant. Now, if we're looking at situations where mostly sort of looking at vertical circles, that would involve a situation where the speed is not constant. So we're not really going to be looking at motion in a vertical circle. We're mostly going to be dealing with horizontal circles or orbits around, say, Earth or planets around the Sun, those sorts of situations. So this is the scenario that we're going to be dealing with. So the speed is always going to be constant. We're not going to see a variation in the speed. In the case of uniform circular motion, there is a defining characteristic that we should be aware of, and that defining characteristic has to do with the force that is involved. And we can identify that that force has a particular direction that we need to be aware of. So the defining characteristic of uniform circular motion is that the force that acts on the object is always going to be perpendicular to the velocity of the object. So whenever we've got a situation of circular motion, a uniform circular motion, that force that we'll be dealing with will always be perpendicular to the velocity of the object. So to make that a bit clearer, we'll have a look at a diagram just to draw attention to that in particular. So this diagram here representing the path that the object is going to be travelling, and we'll identify here that this is actually a bird's eye view, so looking down on top of the motion, so considering it's in a horizontal circle. So if we start out with the object on this side, its velocity is going to be in this direction. Now, velocity being speed in a given direction, so the length of that arrow representing the speed, and then the direction of the arrow representing direction of the velocity. We can consider then the force that's acting on this. We know that the force has to be perpendicular to the velocity, given that it's uniform circular motion. That means that it could either be out that way or that way. Now, we can determine based on the direction of motion that it has to be this one that's directed towards the left here, not the one to the right, because given that the speed's going to be constant, the effect of the force is going to be to change the direction of the velocity. So if the velocity sort of, the direction is curving over to the left, we know that the force that's acting on it must also be towards the left. That then means at some later point in time the object will be sort of at the top of this circle. We know that the length of that vector is going to stay the same because the speed is constant, and we know that the force is still going to be directed perpendicular to the velocity, so it's going to be in that direction. Again, as it continues to move around over this side, the velocity will still have the same speed, so the length of that arrow is still the same, and the force will still be perpendicular, and the force itself will still be the same magnitude as well. And finally, down the bottom location here, velocity will be to the right now, still the same speed, and the force will be directed up with the same magnitude. So you can see there the direction of the force is always perpendicular to the velocity. A little point to note here is that since the velocity is always changing direction, the force is always changing direction as well. So while the speed is constant, the velocity is going to be varying because its direction is changing, and that also means that the force will change direction as well. But we always have that relationship that the force and the velocity are going to be perpendicular. So there's some of the basics about uniform circular motion. The next thing that we need to look at then is to have a look at the speed itself. We can determine the speed by considering one full revolution of the motion of the object. What I mean by revolution here is the time and the distance covered for the object to go one complete circle, and makes it a bit easier than trying to consider some sort of random displacement or random amount of time that's passed. So one complete revolution is what we'll be looking at. Just a side note here as well, just to be aware that the term revolution means to move around the center of motion of a different object or a different body, and the idea of a rotation is basically revolving around your own center of mass or the center of your own body. So if you think about the Earth would complete one revolution around the Sun in 1 year, it completes one rotation in 1 day. So just be aware of those two different terms, and just to make sure that you're aware of that whenever we come across a few questions, given that those two terms can have very different effects depending on whether you're considering the rotation or the revolution of an object. So now if we consider what's happening here as it moves around a circle, the distance travelled by the object will be the circumference of the circle. We can then figure out what that distance is by considering the equation for the circumference of a circle. And so we have then that the distance is going to be 2 pi r. Remember here that s represents distance. Note that I'm not putting an arrow above it. We're not talking about the displacement, we're talking about the distance the object has travelled. Now the time taken to complete one revolution is known as the period. It's a term that we've come across before when we looked at wave motion, and has the same sort of meaning. It's basically sort of the time to complete one full motion of the object, and in this case it's to move completely around the circle and back to its starting point. So if we consider time being t, in this case that value of time is going to be equal to the period capital T. And since average speed then is calculated simply by distance over time, or otherwise the rate of change of distance, we have a fairly simple equation we can start with at least. So that rate of change of distance, we can consider it to be that v is equal to s over t. So again, noting that this is the speed that we're dealing with here, not the velocity. We're not looking at the vector quantity. If we make those substitutions, we then have that v is equal to 2 pi r over capital T. And that's one of the equations in the data booklet, so that's specific to circular motion. So v equals 2 pi r over t tells us the speed of the object as it moves around a circular path. To look at a fairly simple example that involves that equation, imagine that we have a child on a carousel, and that carousel has a certain distance that they're going to be riding from the center, so at a distance of 2.5 meters from the central axis, and completing a full revolution every 12 seconds. So we have a couple of pieces of information there that we can obviously use. The question there would then be to calculate the speed of the child. And we can do that very simply, and we'll do that first of all by considering a diagram here. So if we look at the circular path that's going to be travelled, the radius of that path is 2.5 meters. The child is actually positioned here and they're moving with some speed. We don't know that yet, being v, so that's what we're trying to calculate, but we do know that the period is 12 seconds, so it takes a total of 12 seconds to complete one full revolution. So the data that we've got from the question that we can jot down first of all is that the radius is equal to 2.5 meters and the period is 12 seconds. So it's a fairly straightforward case then of just substituting straight into the equation v is equal to 2 pi r on t. So v is equal to 2 pi multiplied by 2.5 divided by 12, and that gives us an answer of 1.3 meters per second. Now obviously you can use that equation to figure out various other things. So if you know how long it takes and you know what the speed is, you could figure out what the radius of the orbit is, or the radius of the motion. So fairly straightforward calculation that you can use in a few different ways. Obviously we'll take that a step further when we look at some of the other quantities associated with circular motion, and we'll see that in the next video.